All right, hi everybody. Learning from mistakes is an important part of science in general and also life. And today we're going to be applying that idea to data structures. Specifically, I want to talk to you about filters. You might have heard of Bloom filters before. Filters like Bloom filters are used everywhere in all sorts of large-scale applications. For instance, in De Bruijn graph traversal. A filter takes in a set S and then it answers queries for us, whether something or not is in that set. So it'll say yes or no for us. And the conventional wisdom tells us that filters will improve performance at the cost of making mistakes rarely. It'll rarely give us the wrong answer, and that we can guarantee this. But that conventional wisdom is a little bit wrong, and that's what my talk's going to be about today. And for the filters that people have been using for 50 years, that guarantee doesn't hold. Sometimes these mistakes that we might make are common or even certain to occur. And when these mistakes happen, they can break our analytical workflows. And so I'll show you why this happens and how we can fix it. First, I just want to go over what a filter is in a little bit more detail. We have elements in a universe. Those are going to be represented here by fruits, and then our set is the fruits that we have in our basket. And so we want to answer the question, what's in our basket? And so a bad solution to this problem would be just to list all the fruits on a big list. And the reason this isn't a good solution is because it takes too much space. We need log U bits for everything we write down on that list. This might not fit in RAM. So instead, we use a solution called a filter. To extend the fruit metaphor here, we can kind of imagine taking those fruits and baking them down into a pie, which gets rid of some of the individual information about each of them. And so the nice thing about this data structure called a filter is that it only uses log of 1/epsilon bits for each of the entries. And epsilon is a parameter that we choose. So we can choose this so that it fits in RAM. And so if we ask about an element that is in our set, the filter will always give us the right answer. It'll always say yes. But if we ask about something that isn't in our set, we might be wrong. We might be wrong with probability at most epsilon, that's our parameter. And then otherwise we might say no. You can think about this like the filter's only keeping some information about each element. So maybe that apple that's in our set, it only kept the AP of the word apple. And so later if you ask, is there an apricot in my set? It says AP. Yes, I have that. So that's the kind of mistake it might make. Okay, where can filters help us? Well, in many scientific applications, we have a lot of data that's stored in a key value store or a database on disk. And so we'd like to query to get information from our database. And so we might want to list the properties of some elements, some key in our data set. But if the key that we're looking for isn't in that key value store, well, then we have to go all the way to disk and then all the way back before we find out it's not there. We wasted a whole bunch of time. So the hope is that filters can somehow help us avoid that disk access, and I'll say why in a second. So I just want to say again that one of the example applications where we might do something like this is in De Bruijn graph traversal. So the idea here is that our application will query something, but instead of going right to disk right away, first we check with a filter that has the set of all of the keys that are in our database. So if the filter tells us that this key is not in the database, we don't need to go to disk. We save that round trip, we save time. And if that epsilon guarantee holds, we should be able to avoid those disk accesses for nearly all of the negative queries that we want, anytime we ask about something that isn't in the data set, in the database, excuse me. So the nice thing here is we can think about this as a service level agreement, that we only let bad queries go to disk very rarely. And so we can design a system that's built on this assumption. We can have that guarantee that our system is based on. And there are many filters that give us this sort of guarantee. But like I said before, these filters don't actually maintain this guarantee in all circumstances, and I want to give you a couple of examples of where they might fail. The first example is where we have an adversary that's querying our filter. So in this example, our adversary queries something that's in the set and the filter gives us a right answer, then it queries something that isn't in the set and the filter correctly says no. But eventually it queries something that's grape here that wasn't in our set and the filter makes a mistake and says yes. Once the adversary knows this, it can just keep saying grape, grape, grape over and over again, and we'll get a wrong answer every time. So our false positive probability tends towards 1. That's bad. Another example is where there's no adversary, there's no evil mastermind, but our queries follow a skewed distribution where some of them are much more common than others. So if we get unlucky and one of the really common ones is a false positive, well, then we get a false positive a lot of the time. We break that guarantee again. So this is a fundamental problem of these filter data structures. They're static and the representation doesn't change, so they're doomed to repeat their mistakes forever. So I'm going to show you how we can build a filter that doesn't run into this problem. First, I need to describe to you how one of these static filters works. This is called a quotient filter, and a quotient filter is essentially just a fancy hash table. So when I want to insert an item into my hash table, into my filter, like this apple, I'm going to run it through a hash function that spits out a bit string for me. I'm going to split up this bit string into a couple pieces. The first piece is the quotient, which is log n bits, and the next is the remainder, which is the next log 1 over epsilon bits. The quotient tells me where to look in my hash table, and I just store the remainder there. So in this example, you can see we go to that location, and we store the remainder 0100 in that location. So I've inserted the apple into my filter there. And I just repeat this for every item in my positive set. I populate this hash table, and now I'm ready to answer queries. And so whenever I query some element X, I hash it through the same hash function. I find its remainder. I go to that location, and I check the quotient to what's there. If they match, I say yes. And if they don't match, I say no. So let's go through just a couple examples here really quickly. First, I'm going to query this melon slice or whatever that is, and that's going to point me to a location where I don't have anything written down. So that's easy. I know that that's not in my filter. And then next, I'm going to query the apple. That truly is in my positive set. So I know that if I go to that location, that remainder is going to be what's there, because by construction, that's what happens. And so in my final example here, we have a false positive where I query the grape, and I go to that same location, and notice how its remainder and quotient exactly match the remainder and quotient of the apple. I just got a hash collision. I got unlucky. And so now that means that that's why my filter is going to incorrectly say yes. Okay, so that's how a static quotient filter works, omitting a lot of details, and that's how we can get a false positive. So the reason I said all this is because conceptually, the idea about how we can fix this mistake is truly very simple. When I notice that I get the false positive from the grape and that it clashes with the apple, I'm going to go back and hash out the string for the apple again. I'm going to add on extra bits until one of them doesn't match the extra bits for grape. I'm going to extend my remainder out by that much in my hash table. Now I know that if I ever query grape again, it will never be a false positive because I went in and I fixed that specific false positive. And in expectation, you only need to extend it a constant number of bits to make this correction work out. So we built this and we tested it on some different applications. And so I briefly want to describe what we learned about this. The first nice thing that we can say about this is that it just holds up that epsilon guarantee of failure, no matter what query sequence you give it, and no matter what weird stuff you throw at it. And so we find the first nice property that it gives us is even if nothing funny is going on, as you run your filter, as you get more and more queries, your false positive probability is going to go down because it's going to make mistakes and it's going to learn from them. And so we show in one experiment that you don't need to even gain that much space. You don't need to add that many bits before you get a huge reduction in the false positive rate. And in some database applications we tested this on, we got a 4 to 7 times speed up. And we also show that adaptivity is essentially free. You want your filter to be fast, right? You want insertions to be fast, you want queries to be fast, and you also want to give it good. You also want it to be giving good answers. And so here we compared it against another type of adaptive filter that doesn't have strong guarantees, and then a static quotient filter. And we can see for several different micro benchmarks here, where we're trying to insert lots of elements very quickly, or we're querying from a uniform distribution or querying from a skew distribution, like I mentioned before. In each case, we either match or outperform the state of the art. So these are benefits that we get in addition to or on top of the stronger guarantees than these existing systems. The most dramatic example I presented before was when there was an evil adversary that was trying to defeat our filter. So we ran some tests just to make sure that it works in that case too. And in this test, we vary how much of all of the queries that the filter is getting are controlled by the adversary. So the higher a percentage of queries that the adversary can make, the more powerful it is, the more problems it can cause your filter. And their task really is to find enough false positives to fill up the cache in your system, because the cache is sort of like a poor man's adaptivity. If it made a mistake recently, even if the filter doesn't learn from its mistakes, the cache might still remember anyway, so you don't need to go to disk. So we found in these experiments that it's a little hard to see because we did so well. We're suffering from success because the line, how well we do in terms of queries per second is just a horizontal line. So it looks like one of the axes, but that's because we have this guarantee. We don't get worse even as the adversary throws more and more stuff at us. So that's the dark horizontal line you see there. And all these other lines representing other systems are kind of scaling down over time. As the adversary gets more powerful, they do perform worse. So finally, I just want to say, okay, great. I just want to say that you can scale up scientific computing by building systems that rely on these guarantees. And so we're looking for more applications that could benefit from these. So here's a couple properties that an application might have where this would help. If you're already using filters like Bloom or something else, we might be able to help you. If you make frequent or expensive lookups to disk or over network, or you have to do heavy computation to figure out if something exists, maybe a filter can save you some of that. If you have potentially adversarial users like green power grids, where you have people trying to supply power to the grid, but they could be doing something weird, that might be an application. And then finally, if you have skewed grid distribution. So if any of this sounds like something you have, come and talk to me. I'd be very interested to hear more. All right, thanks for your time.